Good afternoon, everyone. I am Yuan Salazar Jovita, a grade 11 STEM Larung student from Floreta Herrera Irizarry National High School. And for today's video, we will discuss about the topic that we had tackled this second quarter. So, to start with, there are two types of weathering, the physical weathering and the chemical weathering. Let's define first what is physical weathering. Physical weathering refers to the breaking down of rocks and minerals without changing its chemical composition. There are 6 types of physical weathering: frost bridging, salt crystal growth, abrasion, biological activity, exfoliation, heat and cold cycles. Second type of weathering is chemical weathering. So what is chemical weathering all about? The breaking down of rocks and minerals caused by chemicals in rain or moving water leads to rocks change in chemical composition or weakening of its structure. There are 3 types of chemical weathering: dissolution, hydrolysis, and oxidation. At this juncture, let us talk about the Earth's hot interior. What is the source of the Earth's internal heat? The Earth's internal heat provides energy for our dynamic planet. It is a driving force for plate tectonic motion and for ongoing catastrophic events such as earthquakes and volcanic eruptions. So, there are 2 sources of Earth's internal heat. First is the primordial heat, and second is the decay of long-lived isotopes. Primordial heat composed of accretion energy, adiabatic process, core formation, and lastly, decay of short-lived isotopes. So now, let's proceed to the decay of long-lived radioisotopes. This illustration is the distribution of Earth's internal heat. So now, our next lesson is about magma formation. So what is magma? Magma is composed of molten or partially molten rock which is stored under the Earth's surface. When magma reaches the surface, it is referred to as lava. Magma formation. Magma is formed when hot rocks in the earth partially melt, which occurs when first, the pressure decreases, second, volatiles are added to hot rocks, then third, heat is transferred by magma rising from the mantle into the crust. Magma also forms when 2 processes occurs. So the first process is the decompression melting. Decompression melting is the process of creating magma by reducing the pressure at a constant temperature, while the second process is the flux melting. It occurs upon the introduction of volatiles, which breaks the chemical bond in rocks and at the same time lowers the melting temperature of the rocks. So this is the illustration of magma. So now let's identify why and how magma rises. Density contrast, magma rises faster when the difference in density between the magma and the surrounding rock is greater. At deeper levels, magma passes through mineral grain boundaries and cracks in the surrounding rock. When enough mass and buoyancy is attained, the overlying surrounding rock is pushed aside as the magma rises. Depending on surrounding pressure and other factors, the magma can be ejected to the Earth's surface or rise at shallower levels underneath. So now, at shallower levels, magma may no longer rise because its density is almost the same as that of the country rock. One reason why magma rise is because of the viscosity. Viscosity measure of a fluid's resistant to flow. Magmas with low viscosity flow more easily than those with high viscosity. Temperature, silica content, and volatile content control the viscosity of magma. So these are the factors that affect magma's viscosity. If the temperature of magma increases, automatically the viscosity decreases. So now let's proceed to metamorphism. Earth's internal heat is a driving force of many processes. Some of these processes are formation of magma, movement of plates, earthquakes, and eruption of volcanoes. So in this video, what I am trying to point out is that we will focus in one process called as metamorphism. So let us define metamorphism. Metamorphism is the process where a pre-existing rock transforms into another form of rock. Alteration of minerals, changes in crystalline texture. One example of metamorphism is this illustration. One of the causes of metamorphism is the fluids. Metamorphism can significantly alter a rock's mineralogy by introducing or removing chemical components that dissolve in water. Pressure also causes of metamorphism. Minerals that are stable at a lower pressure near Earth's surface become unstable and recrystallize to new minerals under the increased pressure at depth in the crust. Let us talk about the grade of metamorphism. Metamorphic grade is a general term for describing the relative temperature and pressure conditions under which metamorphic rocks form. So now, let us focus on the types of metamorphic rocks and metamorphic phases. There are two types of rocks. It could be foliated and non-foliated. Examples of foliated rocks are slate, phyllite, schist, and gneiss. While examples of non-foliated are amphibolite, hornfels, quartzite, and marble. Foliated metamorphic rock. These have a planar foliation caused by the preferred orientation, alignment of minerals. Presence of foliation is caused by they have a significant amount of sheet silicate exposure to differential stress. Differential stress like tension, compression, and shearing. Here are the examples of foliated metamorphic rock. First is slates. The second one is schist. And lastly is gneiss. Non-foliated rocks lack a planar fabric. Absence of foliation possible for several reasons. First, rock not subjected to differential stress. Second, dominance of equant minerals like quartz, feldspar, and garnet. Then third, absence of platy minerals, sheets, silicates. So now, let's proceed to the metamorphic phases. Groupings of rocks of various mineral compositions formed under different grades of metamorphism from different parent rocks. Example of these, zeolite, blue schist, eclogite, amphibolite, green schist, granulite, hornfels, saninidite, and others. Let's now move on to continental drift theory. So the predecessors of the continental drift theory, contracting Earth theory, it is the cooling of the Earth caused contraction, and the pressure produced by contraction caused some parts of the crust to buckle upwards, forming mountains. Other parts of the crust buckle downwards, creating ocean basins. The second one is expanding Earth theory. Many people suggested that the Earth's size started small, but different mechanisms caused its expansion. From Pangaea to Jurassic era, next Cretaceous, and lastly modern era. In 1912, a meteorologist who named Alfred Wegener proposed that the continents had once formed a single landmass called Pangaea before breaking apart and drifting to their present locations. Here are the main points in the continental drift theory. 200 million years ago, Pangaea split forming Laurasia and Gondwana. Laurasia composed of North America, Europe, and Asia, while Gondwana composed of South America, Africa, India, Antarctica, and Australia. Over the past 150 million years, these land masses split and drifted to their present positions. At this juncture, let us talk about the evidences of the continental drift theory. So first, fit of the continents. The coastlines of continents seem to fit with each other like jigsaw puzzles. The second one is fossil evidences. Presence of Glossopteris, Mesosaurus, Cynogatnus, and Lystrosaurus fossils in different continents. So now, let us know what are the criticisms of the continental drift theory. First, lack of explanation why the continents are drifting. Second one, Wegener is a meteorologist and not a geologist. Then third, error in calculating the movement, because according to history, there is an error in calculating the movement. So now, let's go on to our topic, seafloor spreading hypothesis. Alfred Wegener's continental drift theory was not highly accepted during that time for so many reasons. In the year 1962, Harry Hammond Hess proposed the seafloor spreading hypothesis. This theory confirmed the idea of Wegener and explained the movement of continents due to seafloor spreading. The seafloor spreading hypothesis. In 1945, Harry Hess measured the depth of the seafloor using a sounding equipment. Hess discovered features on the floor of the ocean that appeared to be mountains with the tops flattened. In 1953, the Great Global Rift was discovered and inspired Hess to re-examine the data that he collected while at sea. History of Ocean Basins was published in 1962 and explained the mechanism behind Alfred Wegener's continental drift theory. So we can see in this illustration that the movements of the continents is caused by the seafloor spreading, and one of its mechanisms is that hot magma rises from the rift, pushes the plate, and also new seafloor is generated in the rift. Old seafloor subducts as it converges with continents. And now let's go on to the age of the ocean floor. So older seafloor is present as you go farther away from the mid-ocean ridge. Take note that our planet is 400 billion years old. So now let's continue to our topic, seafloor spreading hypothesis. Magnetic striping rising magma assumes the polarity of Earth's geomagnetic field before it solidifies into oceanic crust. So we can see in this illustration from 0 million years to 1 million years until 2 million years. So now let's talk about the ocean basins. Ocean basin refers to any of several vast submarine regions that collectively cover nearly 3/4 of Earth's surface, containing almost all of the water in our planet. And these are Pacific, Atlantic, Arctic, Indian, and Southern. In evolution of the ocean basins, there are 5 stages. First is the embryonic stage, where a continent breaks apart because of the uplift. The second one is juvenile stage, where rift valleys gradually widen and eventually connect to the ocean. Next stage is the mature stage, with continued lateral spreading of the rift valley. The divergent plate boundary widens and additional oceanic crust is generated. And the fourth stage is declining stage, where subduction becomes more widespread around the border of the ocean basin. The next stage is the terminal stage, where the ocean basin closes through subduction as continents from opposite sides of the ocean basin bear down on one another and eventually collide. And finally, the last stage is suturing stage, where collision of the continents is complete and the intervening sea is gone. So now, let's proceed to our next topic, which is plate tectonic theory. At this juncture, let's have a short recap. We all know that Alfred Wegener composed a theory which is continental drift theory, and Harry Hammond Hess also composed seafloor spreading hypothesis. So now, let's talk about the plate tectonic theory. So to start with, a plate tectonic theory is a collaborative theory that composed of many geologists and scientists. Here is the illustration of the 4 sublayers of the Earth, which is the crust, the mantle, the outer core, and the inner core. The plate tectonic theory states that the Earth's solid outer crust, the lithosphere, is separated into plates that move over the asthenosphere, the molten upper portion of the mantle. Plates are composed of lithosphere, about 100 km thick, that float on the ductile asthenosphere. So, in the illustration, here are the examples. First is the plate 1, second is the plate 2, and third is the plate 3. So here are the major and the minor plates. So there are 7 major plates. And it is Eurasian plate, Pacific plate, North American plate, South American plate, African plate, Australian plate, and Antarctic plate. And there are 3 minor plates. These are Juan de Fuca Plate, Nazca Plate, and lastly, Scotia Plate. Plate boundaries is simply defined as the edges where two plates meet. There are three types of plate boundaries. First is the divergent plate boundaries, where plates move away from each other. The second type of plate boundaries is convergent plate boundaries, where plates move toward each other. The last type of plate boundaries is the transform plate boundaries, where plates slide past each other. So in this illustration, we can know what is the cause of plate movement. Convection currents in a stratosphere is a semi-solid. And in this illustration, hot rising currents can cause why plate move. Our last topic to discuss is about relative dating. Relative dating is used to arrange geological events and the rocks they leave behind in a sequence. The method of reading the order of rock layers is called stratigraphy. According to Nicholas Steno, there are 4 laws in relative dating. First law is superposition. The second law is lateral continuity. Third is original horizontality, and lastly, law of cross-cutting. Law of superposition states that in an undeformed sequence of sedimentary rocks, each layer of rock is older than the one above it and younger than the one below it. So G is older than F is older than E, and D is older than C, and so on. Next is the law of lateral continuity. This law states that if layers are deposited horizontally, then it is expected that they are laterally continuous over some distance. Third law is law of original horizontality. This states that rock layers form in the horizontal position, and any deviations from this position are due to the rocks being disturbed later. Finally, the last law is law of cross-cutting. This law states that any feature that cuts across a rock layer is younger than the rock layer it cuts. So now, let's proceed to principle of inclusion. Principle of inclusion states that inclusion found in other rocks or formations must be older than the rock that contained them. The second one principle is principle of unconformity. This principle states that if a rock layer is missing, then there is a missing record of time or the presence of unconformity. Unconformity is a surface of non-deposition or erosion. So now, let's talk about the law of faunal succession. So this law states that fossils occur in definite, invariable sequence in the geological record. So as we can see in this illustration, from younger to older. That is the end of our discussion. Thank you for listening.